So, guys, thank you for coming. We welcome Yusuf. I never know how to pronounce correctly your surname.
January.
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 It's not it's January. January. Thank you. So, Yusuf January. He's a brilliant researcher from Norway, one of the top scientists in Norway. I mean, young scientists in Norway nowadays. So, which place you have in Norway? In terms of science ranking of scientists?
Yeah, in terms of publication, it's top 11.
Top 11. Young or all?
All
scientists in Norway, so it's very good. Just became an associate professor at the University of Southeastern Norway, and he works for North Institute in Oslo, and an expert in machine learning. Enjoy the talk. Thank you very much for coming. And you said he's starting a position with us soon when the paperwork is ready. He's going to come to us every month for a few days from Norway. So, well,
thank you.
I hope it's going to be a very nice and productive collaboration.
Yeah. So thank you, Thomas, for the invitation. Hello, everybody. Today we will show algorithms, applications, and challenges of modern recurrent neural network. So start with the difference between a simple neural network and a deep neural network. So for the simple neural network, so a neural network aims to learn a mapping between input data and output data. So it's kind of learning a function that correlates the input with the output. So it is composed by a graph where we have the input layer, we have some few hidden layers, and we have output layer. And we have a connection between layers. So we inject the data, the input data here, and we have the output data for learning. And we can have a weight between two consecutive layers, where here we try to find the output of each node using activation function. So the idea is to first initialize the weight of the network, and where we inject the input data, we compute kind of output, and we compare it with the real output, which is the ground truth. And with this error, we determine the gradient. And from the gradient, we have this formula of the famous formula for weight updating rule. So which updates the weight of this iteration according to the previous one. And we update the weights according to the big propagation. And we do this for each data in the training. And the main goal is to optimize the weight of the network. However, for the deep learning, it is the same process, but here we have many. So it is a deep. So we have many connections, and it is kind of complex networks. So we have many connections between nodes of consecutive layers, and also we have many layers. So now we talk about the recurrent neural network, so which is a kind of one type of deep learning that learns from sequence data. So in our daily life, we can have sequence data in many applications. For example, in the speech recognition, where we try to recognize recognize a sentence of the speech of the signals. So the input data will be a signal, which is a sequence data, and output will be a sentence of the speech. We can have it in machine translation, where we want to translate a sentence from another. For example, translate English to Polish. We can have it in video activity recognition, when we try to according to the frame, a sequence of images, we try to recognize an activity of what happens and what happened in this frame. So we can have it in many applications. So the recurrent neural network principle. So the idea is to learn from sequence data. So we have the sequence data, and the sequence data is a set or a sequence of elements, and we want to learn from this sequence data. So the recurrent neural network is composed by a set of cell states. This is a cell state. So it is composed by a set of cell states where in each cell state we will learn one element in the sequence. But not only this, we will also learn the connection between the elements in the sequence. So we want to learn kind of the correlation between the different elements in the sequence. So, and this connection should be transferred, should be verified by the transformation of the knowledge from one cell state to another one. So this is an example of how we can apply the recurrent neural network in one application. For example, in named entity recognition, where we have a sentence, and for each word in the sentence, we want to recognize the entity. So if we have, for example, three classes, three entities, person, location, and other. If it is not person, it is not location. And we have this RNN, simple and not RNN. So if you have, for example, a sentence in Polish, Józef Mieszka w Oslo. Yeah. So if we want to recognize the entity of each word in the sentence, we of course take 4 cell states. So here there is 4 words, 4 cell states, and we want to learn the weight of each cell state, but also we want to learn the weight between 2 consecutive cell states, because for example, the word Mieszka, it depends. The entity of Mieszka depends to the entity of the first word, which is Yusuf. So this connection is very important, or correlation is very important between the element of the sequence. But the main problem of machine learning, and particularly for recurrent neural network, is the vanishing gradient problem. So what is the vanishing gradient problem? So it's a common problem in machine learning where we have, for example, here we have 4 states, and we have the weights of the state. And if you want to compute, to update the weight of the cell state 4, we need to compute the gradient signals of between 4 and 1, between 4, 2, 4, 3, and 4, 3. So, but the gradient signals, according to the chain rule, the gradient signals between 4 and 1 depends to all gradient signals between 1 and 4. It means that it depends to the gradient signals between 4, 2 and 4, 3. And the problem now is if these values get smaller, because these values are between 0 and 1, if these values get smaller, then these gradient signals became smaller and smaller. So if we have, so it means that with the vanishing gradient problem, we will take about short dependency. So we will not have effect for long dependency. So because the weight, the gradient signals between 4 and 3, it will be much higher than the gradient signals between 4 and 1. So we will focus more on short dependency, not long dependency. And this is a problem in machine learning, especially in sequence data analysis. For example, this problem of of prediction word in the sentence, if you have this problem, the writer of this sentence, the writer of the books, and we want to predict if it is or are, we are, as human, we know that it is because we are concentrated with the writer of the books, not the books themselves. So the correct answer is. But according to the short dependency, the correct answer, the answer of the model, if you take short dependency, the answer of the model will be R, because it is focused on the books, not the writer of the books. And this is a problem in sequence data analysis. To balance between short dependency and long dependency, we propose, or researchers developed a new improved recurrent neural network, which are based on gating mechanism. So the most well-known network are LSTM and GRU, gated recurrent units.
The second abbreviation is particularly interesting to Tomek, I believe.
No idea what GRU means.
Gated recurrent units.
Oh, yeah, that's what it means. Yeah, right.
It's a Russian secret service.
Okay, no, it's a gated recurrent unit.
Foreign secret service.
Okay. Yeah, so let's start with LSTM, long short-term memory. So for the LSTM, so for the recurrent neural network, so we have, so we try to optimize weight for, so in the cell state, we have one gate, one way to optimize for each cell state. But in LSTM, we have 3 gates. Inside each cell state, we have 3 gates to learn. We have, the first gate is a forget gate. This forget gate simulates how much information we will forget in this cell state. The input gate, we will simulate how much information we will keep after learning this cell state. And the output gate, we will learn, or we will combine both the forget gate and the input gate to construct the information of the gate, of the information of the next gate. So let's start with the forget gate. So why it says forget gate? So first we have the current element and the information of the previous element. We do kind of concatenation and inject it to activation function, and we combine it with the previous set state. So we combine it with multiplication. So we know that after the activation function, the value is between 0 and 1. And when we do the multiplication, the value will be less. So we will decrease for the value received. It means that we forget the information that we want that we have. So with the multiplication, we simulate how much information we will forget. It will be the same as for the input gate, the same process, but the result we will add it we will add it to the previous cell state. So if we add a value and this value between 0 and 1, we will get much higher value. So it means that we will simulate how much information we will keep in this cell state. And the output gate, it will be a combination between the result of the input gate, the forget gate, and the input gate. And we will have the result of this cell state that will be used as information for the next cell state. So now for the gated recurrent network. So for the gated recurrent network, so it is kind, we can call it compressed LSTM. So instead we have 3 gates, we have 2 gates in the cell state. So we have update gate and reset gate. So The reset gate, it is the same as forget gate. So we have a multiplication. But the update gate here is a combination between update gate and output gate of LSTM. So if you have a problem now, and we have both short dependency and long dependency, we will use even LSTM or GRU. But what is the best model that we want to use? So researcher, so we don't have a clear answer for that. So for example, if we have a problem where the inference time is critical, then it will be interesting to explore GRU, because GRU is compressed LSTM and it is fast in terms of runtime processing, since we have a few parameters compared to LSTM to optimize. However, the researchers suggest that if you have a problem, we start with LSTM. And if the performance or the accuracy is good and everything is good in terms of quality of the learning, we will try to design a completed GRU from the designed LSTM. So this is approach to explore LSTM and GRU for sequence analysis. Now go to the application of recurrent neural network based algorithms. So we have different applications. For example, in natural language processing, we have the problem of caption generation. So the caption generation problem, so we have an image, and the idea is to automatically generate a caption to this image. So there is a recent study which explored both advanced network for images and also for sequence data or for sentence learning. So explore, since we have images, we have kind of multimodal data. We have images and text here. First, we have the image. We do the resizing to inject it to VGG16 to compute the features, and we inject these features to the STM model to learn the caption of this image. So it's kind of a hybrid model between LSTM and CNN or VGG16. The problem of this solution is that it effectively gives a good result in terms of accuracy, because it combines both the specification of the images and the specification of the sentence, but also it is complex in terms of inference runtime, since we have many parameters to train, and also in terms of hyperparameters. So we need to optimize the parameters of LSTM and optimize the parameter of VGG16. But for VGG16, there is a model, there is an approach, or we can use a pre-trained model to compute the features of VGG16. Now we go to the sequence labeling. So another application of natural language processing, which explore the recurrent neural network. So here we proposed in a recent study kind of advanced LSTM model, which combines attention mechanism with LSTM. We developed a BLSTM, a bidirectional LSTM model to learn from the text data for labeling this sequence of the text data. Now we can, so there is another application of sequence data analysis of LSTM, which is intelligent transportation. So here, with my colleague Thomas, we developed a new concept of trajectory outliers, which are a group of trajectory outliers. So the existing study tried to focus only on individual trajectory outliers. It means that we retrieve trajectories that that deviate from the normal trajectories. And the trajectory could be modeled as a sequence of data. It is a sequence of points. So here we proposed a new concept of trajectory outliers. We will not focus only on finding the individual trajectory outliers, but we will retrieve or study the correlation between these individual trajectory outliers to find a group of trajectory outliers. So we developed kind of several solutions based on data mining and machine learning, and also we explored recurrent neural network to find such group of trajectory outliers. Also, we can have it in sequence traffic correlation, where we have multiple sources in Internet of Things application, and we have kind of different data here, time series data, set of time series, for example, and we can apply recurrent neural network to study also the correlation between this or the irregularities between these two, between a set of traffic data in the IoT setting. We can also have it in smart building, where we, for example, in the activity recognition, because activity recognition data are modeled by a set of signals captured from different sensors. So we can apply it in activity, in human activity recognition for smart building application. Here we proposed, in the context of activity recognition, we proposed a hybrid architecture between a graph convolutional network and a gated recurrence units. So we have different sensors, and we try to model or capture the data from different sensors. So we have different signals for these sensors. So we study the correlation between the different sensors to build a graph or a network of sensors. So we have a graph of sensors, and also we have the temporal information, where the graph, we have the kind of dynamic graphs. So the graph changes across the time. So here we have two dimensions. We have the temporal dimensions, and also we have spatial dimensions by the graphs. So the graph convolutional network, we study or we learn from the spatial dependency of the graph, and GRU we learn from the temporal dependency of the graph. And here we propose a loss function which combines both the loss of GCM and the loss of GRU to better learning from both temporal and spatial dependencies of, let's say, a dynamic graph of sensor networks. Here, so we have different challenges for recurrent neural network. So let's start with the first challenge that we work on. So especially in time series, so we have a large number of points or raw data in the time series analysis. So learning from this raw data became inefficient in terms of time and in terms of accuracy. So it is hard to build a model, a deep learning model, that is capable to learn from this heterogeneous and non-normalized data. So we are working with Professor Imon, which is a professor at the University of California, and it is one of the top scientists in time series analysis. So we are working on building a new representation of time series analysis, which is distribution of time series. So, distribution of time series is not new; it exists, but the learning from distribution doesn't exist before. So, if you have, for example, a real time series data, we divide it into different time windows, and from each time window we build kind of distribution of time series. So it's kind of compressed way of time series representation. So instead of exploring 1 billion, let's say 1 billion of points here, if we have each time window contains one data point, then we explore only 10 million of the distribution of time series. So instead of applying the learning in the real time series data, we will apply it in the distribution of time series, distribution of time series. So we will predict another distribution, we'll classify another distribution, we estimate it, another distribution, we'll find outliers from distribution and so on. The main challenge here is how we can design efficient deep learning models for, or in general AI-based models for the distribution of time series. So we need to take a specification or characteristics of the distributions, mathematical modeling of the distribution, and from that we will think about new or innovative deep learning models, for example, to find or propose a new loss function or a new architecture or everything for distribution of time series. The last challenge that we want to explore is trustworthy AI or explainable AI in industrial production data. So we work with NTLC, which is a leading company in Norway, focused on industrial production data, prediction models. So if you have the industrial production data captured from different tags or sensors in the factory, and we try to predict one variable that are not in this industrial production data, and apply a prediction model to predict this variable. So this is a prediction model. But the problem here is how we can use XAI to compute first the contribution of each features or each time window in this industrial production data, in order to prune the data for the future, for future learning, for further learning. Because in order to kind of reduce the number of tags in the network and reduce the number of sensors in the networks, and give the operators actionable insight for the data that we have. Yeah. Thank you for your attention. Is there any questions?
I have a few, but these are not very concrete since I am not really, sorry, I don't know much about this topic, which just shows me that I will have to just get more knowledge. But so you said about those LSTM and GRU, right? I assume that the fact that GRU is considered to be the go-to method if you want to have some efficiency tweaks, that this one is more complicated to implement actually, or more difficult to use. Could you elaborate maybe how do these two differentiate when it comes to actual usage of them?
Good question. So the problem, the difference between GRU and LCM is not the main problem is not related to the implementation side. So for the implementation, so we have efficient libraries in Python or in to make the implementation of these models. But the most important is that LSTM, it is not it is proved, but by experiments, by exploring different use cases, researchers assume that LSTM gives good accuracy in terms of gives good performance in terms of accuracy compared to GRU. So, but in terms of inference runtime, GRU is much faster because it is compressed LSTM model. So the question here, how make I'll make a model in between where benefit from GRU and benefit from LSTM in order to optimize both accuracy and inference runtime. This is one thing. Another thing is that so another thing is that researchers starts. So this is the methodology to follow. But of course, we can have other methodology. But a good methodology, I think, is that we start with LSTM, make a model with LSTM, and from that we try to according to our need. If the inference time is okay, so it's okay. If the inference time is high and is critical for this application, then we will go to kind of compressed LSTM from our model to GEAR.
Okay, I see. Thank you. You have cited the illustrated guide LSTM and GRU. So would you say you recommend this source to get more knowledge on that topic if I want to pursue it myself? Which on those slides where you have those animations.
Okay, yeah.
Yeah, so you've got this illustrated.
Because
illustrated guide to LSTM.
Yeah.
Would you recommend just going through this guide by myself?
Yeah. So this is first of all, why I mentioned this because these animations.
I know. You took them exactly from that.
But
the course itself, however, is it good?
Yeah.
It's good.
I learned a lot from this course.
Okay, thank you. Do I need some previous research or to how extent?
For this course, just some knowledge in deep learning.
Okay, thank you.
So I have a general question. So the question is, why would I actually use recurrent neural networks, especially this year when the transformer is available, and they seem to work. I know they seem to work better. Especially they have like fully parallel training. So especially on large amount of data, they seem to be basically more efficient at training. Could you like address it? Like why recurrent neural networks at all? Because in all those applications, I think like transformers could be used. But so why not? Maybe.
Yeah. So the main problem of the recurrent neural network is the vanishing gradient problem, but it is solved by LSTM and GRU. Yes, transformers now actually gives good results in many applications. But there is an optimization. For example, there is different types of LSTM. For example, bidirectional LSTM, unidirectional. So the question here, can we build a transformer that learns from two directions? This means that from the input to output and from output to input. Yeah, so this is one thing. I don't know if there is a transformer that learns from two directions. This is one thing.
Like not just text to text like translation or
no. Or I mean that we kind of the weight of the network is bidirectional, not unidirectional.
Oh, I mean we have like we can like be bidirectional, and like we we have like BERT, which is bidirectional if you just use encoder in the transformer. So it seems like, unless I misunderstand your comment, it seems to be just an encoder part of the transformer. So like GPT doesn't work like that, but if we want to, we could use BERT, I think.
Yeah.
Or like standard transformer from the original paper for like translation.
Yeah. But it seems like, for example, like why the question is why we use ResNet and not use DASNet for classification, for example. So but for some application, we can prove that LSTM gives better results than transformers in some applications.
Okay.
So we can't ignore one model and focus on other. So it depends on the application also as well.
I see. Can you like point me to like which domains will generally be better suited for RNN or variants of RNN?
To the best of my knowledge, I tried RNN for time series analysis, especially for outlier detection, and gives promising results. And also in anti-agent transportation, also in traffic analysis modeling, it gives impressive results.
Okay, like in comparison to transformers or in general, because
it outperforms the transformers.
Okay, I see.
For this application.
Okay,
some of these applications.
That's nice to hear.
Yeah, but for natural language processing, transformers were developed for many years for natural language processing, because transformers are first developed for the NLP. And I think that, in my opinion, there is transformers for NLP. Transformers are better than recurrent RNN.
I see. Yeah. Okay.
So, thanks. So what about when the like size of the data is smaller? Like because like Sebastian said, like in when we have large amount of data, a transformer surely outperforms the RNN based models. So maybe in the lower regime of data, because we still have this, we still on this RNN, we still have this inductive bias that you like process sequence like element. Yeah, so transformers are more general. So maybe in the lower size of data regimes, does the RNN-based models does they work better than transformers? So yeah, I also like maybe quite like following up the question from the Sebastian. So maybe in this area, are the LSTMs for like €2 better? So that's the question.
Yeah. I think you're absolutely right. For example, and one illustration is the ChatGPT. So the ChatGPT tool is made using a transformer. Is transformer based algorithm model, and they use a massive data for training. And my opinion, if we build the ChatGPT with LSTM, we will not get this impressive results ChatGPT. So because so maybe also according to the data size or to the distribution of the data in the learning space, this affects whether we can use transformer or LSTM. Yeah.
Okay.
Questions? No, thanks, speaker again. Thanks, Sarah. We can talk with you at the lunch.